Well, this is John Black, superchemist, wave particle duality. Just like this clock. How is it acting like a wave? Oh, it's vibrating back and forth. How's this spring acting like a wave? Oh, it's springing back. It's also, they're all oscillating. Same way with this spinny thing, the orbiting thing. It's oscillating. It's a periodic thing. If you have a periodic thing, okay, you can use a wave equation, okay? Doesn't mean it's a wave, okay? This isn't a wave, no wave, not a wave, not a wave, okay? The space ball's not a wave. But you will end up with this, okay? The path, see the path, how it looks like a wave? See the particle, where the particle is, the particle doesn't look like a wave. You know why? Because it's not a wave. Only the path is the wave, okay? The path is the wave function, a mathematical construct. And all it's doing is describing, okay? And what's it describing? It's describing all the paths, right, that you could possibly take, right? And it's assigning a probability, a percentage probability that the particle will take that path. That's it. That's all it's saying. And if you can't take the path to all these, sometimes you can't go to these points. You know why? Because the math says you're a wave. You didn't go in a straight line, so you're hitting stuff, and you got different probabilities on what you can do and what you can bounce off of, okay? I want you to remember always, okay, that sometimes a probability equation, a wave equation, sometimes the probability for that position is 0.
In particular, I want to know, well, if the momentum looks like this, what does it look like in the position basis? Well, we can figure this one out from the de Broglie relationship, which says that if the state is just one momentum, then when you look at that same state in the position basis, it's going to look like one infinitely long sine, and it's going to be traveling at the speed given by that momentum.
You can see she knows when you know the momentum, the position looks like a sine wave, right? Going up and down, looks like that, right? And vice versa, when they know the, you know, when they know the position, the momentum comes out as a sine wave because the electron oscillates. She knows it. Her math proves it. She knows it. They all know it. Okay. Now, what exactly is the wave function, though? Okay. I keep saying that it's the, you know, they take up all the paths that you could possibly go, and you throw a percentage on each one of those paths, and that's the wave function. Well, let's see. I got 9 things on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 things on here. Which one of them is the wave function, and which one of them is not the wave function? Okay. The first thing we have is the electron, right? It's got this wavy path. That's the, you know, because he oscillates as he moves through space, he's going to create this path, right? So, is this the wave function? No. That's a picture of an electron and his path. How about this? It's like a 2-slit experiment, you know, water experiment, or maybe light, electron, whatever. And it's 2 slits here. Is that the wave function? Are these waves the wave function? No. How about this electric here? There's a gap in between this and the wall, and they're going to make electricity jump up this gap, you know, on this plate or whatever. And it, you know, is this the wave function? No. How about this pendulum? You know, it moves back and forth, you know, it oscillates, it makes a sine wave as it goes back and forth. No. That's not, no. How about these here? This one is a multiple thing. It could be customers, right? Customers in the morning, just have a little bit. As time goes on, you got more customers in the store. And then as time goes on, now you got your busiest time of the day, and you got the store filled up, right? Now you have less customers. And then if I did this graph over and over again, right, I would have a space here, right, when the store closed down, right, where nothing happened. Then I would go back to this, where it's in the morning, and we'd have just a little bit of customers, then more, then less, and then we'd have another they close up. So I'd have an empty space at the end, and then it would start again. You see how it would be a sine wave, right? It could be gamblers that are, coming into, gamble. In the morning you have this much, and you have more. It could be anything like that, where, see, a wave function, all it has to do is, it just has to go up and down. It doesn't even have to go up. You can see that it didn't go up. This one's higher than that one, and this one's high. This last one is higher than this one. So it didn't go up and down exactly the same, right? And every day they're not going to have the same exact customers going in there, right? In the middle of the day they're not going to have the same exact number of customers. It's going to vary slightly, you know what I mean? But it'll still go up and down, up and down, up and down, right? That's what makes, this is a wave function. Okay, yeah, this is a wave function. So when I say the electron is spread all out, it's really a wave function. This is what they're talking about. They're talking about a bar graph. This would be the percentages. See, you got a little small percentage here that you're going to have people, a person's going to come into your store or your casino. Here you have a bigger percentage, right? That's what these blocks represent. The percentage, right? Percentage probability that someone will walk through your door during these hours, and here with the longest one in the middle of the day, the probability that someone will walk into your establishment is greatest right here. So it has the biggest number percentage probability. Okay. So what about over here? These two are not, right? This is the wave function, right? Why? Because it represents, what is this? What is the wave? What is the wave? It's a percentage. That's it. It's the percentage of the probability that you'll land on that path, right? That they'll go through two slits. Where are they going to land on this board? Well, you can tell this has the highest mountain. That means that has the highest probability, right? And then as you go down the mountain, you have less probability until you're down to zero probability down here. Then you go up and down and up and down. Yeah, it's just a percentage probability. That's it. Right? That's what the probability wave or the wave function represents. Your probability. That's why they call it a probability wave. It's not an actual wave like going through space. It's a probability wave because it shows the probabilities. The higher your wave is, the more probable you are to do something there. Be the highest number. Be at this spot. Number of customers going through. Percentage that a person will walk through your door. A customer. Percentage. That you'll take this path and land right here. Right. So the wave function doesn't even really show you the paths. Right. It just shows you, it figures out the paths. It doesn't ever show you the paths though. And then it figures out the probability for each path, would go where. You got 90% going here, 30% chance going over here. You got, and then each one of these points would be, for this double slit experiment, each one of these points would be given and assigned a percentage value, a percentage, the chance that you would, land wherever. You know what I mean? So you have so the wave function, okay, is a graphical wave, meaning you put it on a graph, right? It's not a real wave, right? Just like this. See how this is a wave. This is a wave function. It's just a bar graph. All it's telling you is casino probabilities, man. That's all it is. It's a thing used for gambling, you know what I mean? So the same here. This is just, it's more probable that the this gap, the electricity jumps over and it goes more here than over here. You have more probability. It's just a problem. I don't know why people are like, I don't understand probabilities. It's just so magic. It's not magical. Everything is whatever. If I see you can jump 6 feet, and then I see you trying to jump a 5 foot, 11-inch thing, and you can't do a 6 foot one, I know statistically you have some probability of maybe jumping it, but you also have a statistical probability that if you did it 100 times, 100 times, some of those times you ain't gonna make it, because you know what I mean. Because you can't jump 6-foot thing and it's at 5'11". You know what I mean. There's got to be some statistical. You don't understand that, really? Are you retarded? You don't understand when you flip a coin? It's you got the same mass on each side of the coin. You got 50-50 chance. You know what I mean? It's like, you know, if you get a pencil that has a sharp tip and you put the pencil on its tip so it's straight up and down, you don't understand that statistically, you know, yeah, it's going to fall, but, you know, it could go any way. You know, if you have it exactly up and down, you know, probabilities say that you can go fall either way. You know, you know, you have just as much chance of falling this way as that one. What's so hard to, why is that magical? Like, so the wave function is a graphical wave, meaning it's just only on a graph, it doesn't exist. And it's a graphical wave, right, that is on a graph, right? A wave function is a graphical wave that graphically represents the probability of the electron, you know, of taking each path. You know what I mean? What's funny is it doesn't even represent the electron, okay? It only represents, and it doesn't even represents the paths. It doesn't, you know, it represents the probability for each path that you will take that path, okay? You know, to end up, you know, each one of these points has a probability percentage. You got 0% probability here, and that's dot over your. Well, you got 10% probability here. You know, over here, then you get over here, it's like you get, you know, 70, 80, 90% probability. You know what I mean? That's all it represents is each one of these points and the percentage probability that that electron or that photon or whatever will hit there. That's it. Okay. So this here represents the gamblers, the customers, right? The percentage chance that the customer will come into the establishment. Okay. So that's all the wave is doing. The wave function is a graph representing all positive paths, and it's not. It just doesn't even represent all positive paths, like I said. It represents the probability assigned to each path, and it doesn't even do the path. It only does the location at the end. Really, you don't really know what the paths are. All you know is at the end. At the end, at this point, you got a certain percentage probability. Same with all the other points. You really don't even know anything about the path. You just know that magically somehow calculus tells you. And I do believe in calculus. It's great. Don't get me wrong. The wave function is spread out. Okay. Because, you know why? Because it's on a graph. See, you got to. If it was just a dot, see, well, it wouldn't be any good to us on a graph, would it? So to make it any, you know, functional or, you know, helpful, we have to spread out the wave function. See, look, I'm going to spread it out. It was at this dot. Let me spread it out here. Hold on. Now it's spread out. See, it's spread out over the whole area here. So now I can get the information. I can see the probabilities. See how that helps me out? Over here, this used to be a dot too. Now here, I'm going to take it. I'm going to spread it out. Now it's spread out, so you can see. So I can. That doesn't mean the customers. That doesn't make the electron. Okay. It doesn't make the photon spread out. It doesn't mean the gambler spread out. Okay. It means that the graph, the wave function, which is this graph, it's got spread out so that I can actually get some. It was this little, and I grabbed one end of it and I stretched it out that big, and now it's spread out. Yep. So now, why these people can't just say, "Hey, the electron, you know, it jumps up and down, it oscillates." Okay. It oscillates whether it's sitting there, whether it's moving, whether it's, you know, you're talking to it, you know, you're going on a date with it, you're caressing it. It doesn't matter. The electron is vibrating, okay? No matter what, it's vibrating, okay? And that's because that explains your Heisenberg uncertainty thing. That explains this, because as we saw, a wave function doesn't just cover waves, it covers solids that are vibrating, right? Yeah, you can use wave equations for each because they give you the same exact results. Yeah. So now what do they want us to believe, right? Here, I'm going to pretend I'm a woke physicist, right, that believes in magic, and I have to explain everything with magic, okay?